Hello everyone. Today I will present the second tutorial in our tutorial series for the FEBio finite element software. This tutorial is on the topic of unsteady flow past the cylinder. So in this particular tutorial, we're going to create a domain, fluid domain that you see here with a cylindrical opening here, and we're going to look at flow of the fluid going over the cylinder. So we're going to adopt the properties of water. We're going to prescribe what is called a fluid normal velocity load in FEBio for prescribing a velocity of 1 centimeter per second at the inlet. We're going to let the fluid pressure be 0 at the outlet, which in FEBio means prescribing 0 fluid dilatation. We're going to provide a no-slip boundary conditions for the fluid velocity on the cylinder. And we're going to adopt the following dimensions. We're going to let the domain be 32 centimeters long, 16 centimeters high, and we're going to have the diameter of the cylinder be 1 centimeter. But we're going to use SI units, which is why I'm giving you all the dimensions here in units of meters. We're going to evaluate the Reynolds number for the properties of water, the diameter that we're using, the velocity that's prescribed here. It'll turn out that the Reynolds number is equal to 100. So first, I'm going to show you how we create the mesh and the properties that we're going to assign. So we're going to switch to the FEBio Studio software. We're going to create a model. I'll say new model, and I'll select fluid mechanics as the module for it. For now, I'll just keep the default name of model. I'll click OK. And as I said, we're going to pick the units for our problem by clicking on the preferences. I'm going to select SI units, and I'm going to say OK. To create the geometry that I showed you, we're actually going to create two parts. One is called the cylinder in box. That'll be the, for the cylinder geometry. And another one is just going to be a box to the right of it, which actually has the trailing edge of the flow domain. So we'll start with the cylinder, and I'm going to locate the origin of the cylinder at the origin of the global coordinate system. But I'm going to pick the dimensions here. Remember that the width is 32 centimeters for the entire domain, so 16 centimeters for half of the domain for the width and the height. And because FEBio uses a three-dimensional flow analysis, there is no inherent 2D analyses. We have to put a depth to this domain. We'll say 5 millimeters. And the radius of the cylinder is going to be also 5 millimeters since the diameter is 1 centimeter. When I create this geometry, then I will be able to see the domain that you see here. Now I'm going to mesh it. And these are the parameters that I chose. 50 elements along the X direction, 50 elements along the Y direction, 1 element through the thickness because I want to minimize superfluous calculations. And in this radial direction, I'm going to also put 50 elements. I also want the finer mesh around the cylinder than away from it. So I'm going to actually I'm going to actually enter a bias. I'm sorry. I want 50 for NR, and I want to enter a bias here. And I want the elements to actually, from the outer radius to the inner radius, decrease by a factor of 0.93 for every incremented element. This was obtained by trial and error. When I click on apply, you can see that the mesh is much finer on the surface of the cylinder. If I switch to an orthographic projection, you can see a very fine mesh at the center here. So that created the domain for the tube. And then, as I said, now we're going to actually extend this domain to the right of it by creating a box. So this one here is just a box domain. The dimensions are going to be the same for the width, the height, and the depth. 16 centimeters, and 5 millimeters for the thickness. However, I want to locate this box at 16 centimeters to the right of the existing one. So when I do this, you can see that the box was created at the correct location. If I go to mesh it, I'm going to use the same meshing, but there is no cylinder at the center. So just 50 along X, 50 along Y, 1 along Z, and I'm going to say apply. So now these two meshes are continuous, even though the size of the elements right here is not exactly the same, but we will see it will turn out not to be terribly important. Now I'm going to merge these two domains. So I hold down the Shift key and I click on both domains so you can see both of them are selected. And I'm going to select the merge objects icon here. I'll click on that. And I'm going to weld the two so that the nodes which are shared on that common face become unique. And the welding tolerance is 10-6, which is appropriate for the dimensions that I've been using. When I do this, now you see that I'm left with only one object. If I expand the geometry here, there's only one object. If I turn off the mesh and I'm using the keyboard shortcut, the letter M, I turned off the mesh, then you can see that the seam that existed between the two parts is still there. And I can actually get rid of this seam. And it's important to do this before applying any boundary conditions. I'm actually going to rebuild the mesh. And I'm going to scroll down to the options and I'm going to say repartition the elements. When I do this, this seam will disappear because there's nothing, all the elements share the same, are all parallel to each other. So you can see the mesh is still there, but the seam is gone. Let me save this just to be on the safe side. I'm going to put it on my desktop and I'll use the default name model 1. And I'll replace, the model that was already there that happens to be on my desktop. Now that I have the mesh and the geometry, I'm going to create a material. So I go to the material entry in the model tree, and I right click and I say with the mouse and I say add material. Because we picked the fluid module, there's only one choice, which is to define a fluid material. I'm going to select the fluid where the viscosity is that of a Newtonian fluid. I'll say OK. Now I'm ready to enter the properties of the fluid. I can name the fluid instead of the default name material 1. I'll call it water. And I'll enter the properties of water, 1,000 kilogram per cubic meter. The bulk modulus is 2.2 gigapascal, so that's 2.2 e to the 9 Pascal. And for the viscosity, it'll be 0.001 Pascal second. So those are the properties of water. And since this part is already selected, I click on the plus sign, and now the material has been assigned to this domain. Again, I'll save it. So I'm ready to apply the boundary conditions. Remember that the analysis is a 3D analysis in general. So I'm going to constrain the flow to be only in the XY plane. So I'm going to select the front and back faces, and I'm going to say physics, add boundary condition, and later I will use this keyboard shortcut. And I'm going to say 0 fluid velocity along the Z direction. The Z direction is the direction normal to the faces that I selected. So that will make sure that the flow remains two-dimensional. So that is the boundary condition for the fluid velocity on the front and back faces. Now I'm going to select the face of the cylinder, and I'm going to use that keyboard shortcut, and I'm going to say 0 fluid velocity. Remember, we want no slip conditions. No slip conditions, I could also click on Z, but I already selected the front and back faces to say 0, so there's no need to also select Z, although it's redundant and it'll work fine. So now I have the no slip boundary condition. I'm going to select the outlet face, use the keyboard shortcut, and I'm going to say 0 fluid dilatation, which in FEBio means 0 fluid pressure, because the fluid pressure is proportional to the fluid dilatation. The proportionality constant is the bulk modulus, and there's a negative sign that relates to 2. And then I have to click on the box that says dilatation. I have to check this box, otherwise it will not have it. Then finally, I'm going to select, this face, and I'm going to, instead of using physics add boundary condition, I'm going to say add surface load, because I'm going to prescribe now this normal velocity boundary condition. So the normal velocity, I'll click OK, and by default, it suggests a velocity of 1. Normal velocity points towards the outward normal. So in this case, the outward normal to the face that I selected would be in the negative X direction. So I need to put a negative sign to make sure that the flow goes into the domain. And I want the velocity to be 0.01 meters per second, which is the same as 1 centimeters per second, which we said earlier in the slide will give me a Reynolds number of about 100. So at this point, I'm going to leave everything else the same. I'm going to save what we just did, and I'm almost done applying boundary conditions. I actually am going to do one more thing, but I'll show that to you a little bit later. Now I'm ready to set up the fluid analysis. So let me go back to the slides. So what I did is I specified this geometry. I created the cylinder and box with the parameters shown here. Then I created another box that I offset, and I picked these properties for the fluid. Now I selected the velocity of 1 centimeter per second, but going into the domain. So I put a negative sign. And at 1 centimeter per second, I'm going to travel a total distance of 32 centimeters in 32 seconds. So when I set up the analysis, I should run it for at least 32 seconds. But what's going to happen for unsteady flow around the cylinder is that initially the flow will be very laminar and smooth. But after a while, small disturbances will amplify. And as they amplify, there will be shedding of vortices. So if I only wait for 32 seconds, I may not see this slowly increasing, if you want, vortex shedding that we're going to expect. So I'm going to run the analysis to a total of 150 seconds to see whether I can actually visualize this vortex shedding. So I'm going to run it with 1,500 time steps of 0.1 seconds. This is just based on trial and error and some experience with these types of problems. And the Reynolds number, as we said, is going to be the mass density of water times the velocity at the inlet times the diameter of the cylinder divided by the viscosity of the fluid, and that gives us a value of 100. But in order to cause this disturbance and vortex shedding, actually, because this disturbance is generated in the code due to numerical roundoffs, if there are absolutely no numerical roundoffs, the flow could remain very steady, very laminar the whole time. It turns out that numerical roundoff errors will cause the flow to start shedding vortices, but at a later time than 150 seconds. We may have to run the analysis for, let's say, 400 seconds to see the result, and that's too many time steps. So instead, I'm going to disturb the flow. I'm going to cause a flow disturbance very early. I'm going to apply a vertical velocity at the inlet of only 1 millimeter per second, and I'm going to do it in a sawtooth profile with a total duration of 0.4 seconds. So I'm going to switch back here, and I'm going to do exactly what I explained. So I'm going to select this face, and this time I'm going to say physics applied boundary condition. So I'm back to the boundary condition, and I'm going to prescribe a fluid velocity, and I'm going to prescribe it in the y direction. And I'm going to have its magnitude be 1 millimeter per second, which is 0.001 meter per second. So this only gives me the magnitude. And now in order for me to actually produce, to get the sawtooth profile, I'm going to prescribe a load curve, which is a scale factor prescribed on here. So instead of reaching a value of 1 at time 1, I want to reach a value of 1 at time 0.2. Then I'm going to make sure that this curve is linear, because I'm going to just provide, like I said, a sawtooth profile. I'll click a point with the shift key here, and I'll say 0.4 seconds, and I want it to go back to exactly 0. So now I've got a sawtooth profile, a disturbance at the inlet that only lasts for 0.4 seconds out of a total duration of 150 seconds in our analysis. It'll turn out to be sufficient to cause the vortex shedding to occur a little bit earlier than at, let's say, 250 seconds. But by the same token, I'm going to also make sure that my fluid normal velocity rises more or less instantaneously. I'm going to take my time increment to be 0.1 seconds. So I'm going to let the fluid velocity be equal to 1 centimeter per second at the very first time step. Of course, if for some reason numerically it doesn't converge, then I will let the inlet velocity scale linearly from time 0 to time 0.1 in case the code needs to take shorter time increments. So that completes the prescription of all the boundary conditions. Now I'm ready to specify the analysis step. So I'm going to say add analysis step. Again, the only option that's available to me is fluid mechanics. And what I'm going to do now is I'm going to say I want 1,500 time steps. Each time step will be 0.1 second on average. The maximum step size, I want it to be 0.1 second. The minimum, I can leave it at 0.01 or I can make it smaller. It turns out that this particular problem will converge fine with 0.1 seconds, so it really doesn't need to take shorter time steps. I'm going to pick optimal iterations of 50, meaning that I'm not going to take shorter time steps if I converge in fewer than 50 iterations. And I'm going to specify the residual tolerance, which by default is 0. I'm going to make sure that I specify it because I want to use Broyden's method, which is a quasi-static quasi-Newton method. And for the fluid solver, you must have a non-zero residual tolerance. I'm going to only allow 5 maximum reformations of the stiffness matrix, 5 full Newton reformations, which in practice, I will not see any of them. And I'm going to allow a maximum updates, Freudian updates, quasi-Newton updates of 50. To minimize the time in the solver, I'm not going to reform the stiffness matrix if it diverges. If the solution fails at a particular time step, it'll take a shorter time step. And I'm also not going to reform the stiffness matrix at each time step because it'll turn out to be just fine. In most fluid mechanics analyses, we don't need to use these settings. These are the default settings mostly for structural mechanics. Okay, so I have now all the settings done for my solver. When I have selected a solver, then by default, all of the fluid mechanics output variables are selected here. So I wouldn't need to do anything more, except that in this particular case, I would be interested in figuring out the drag force and the lift force exerted by the fluid on the cylinder. So when I do this, I'm going to say edit the plot variable, and I'm going to look for a plot variable called fluid surface force, which is this one. But when I select fluid surface force, I need to add a domain here, which represents the domain on which I want to evaluate the fluid force. And so I don't have any domains available because I haven't defined any. So before I do this, I'm going to close that. I'm going to come back to this model, and I'm going to select the cylinder, and I'm going to go to edit, and I'm going to say name selection. I could have used this keyboard shortcut, name selection, and it calls it by default surface 1, and I'm going to call it the cylinder because that's what it is. So now when I go back to the output and I select this plot file, if I look at the fluid surface force here and I click on add domain, now the cylinder is available. I click OK, you see that the cylinder has shown up. So if you don't specify a domain, then the fluid surface force will not give you anything. Okay. So I am ready to run this analysis. And when I do this, I'm going to say FEBio run, and I'm going to run the analysis. And what you're going to see is that the analysis is running here, and it's converging nicely. And it's already at time 0.4, 0.5. But remember, we want to go to time 150 seconds. So it turns out that this particular analysis will take about 10 minutes to run on the computer that I'm using here. It may take a little longer or a little less on your computer. It depends how powerful your computer is. So what I'm going to do then is I'm going to, stop this particular analysis because I'm not going to wait 10 minutes here. What I'm going to do is I'm going to actually open the file that I already ran. And I'll remind you, based on the first tutorial that I gave you, if you don't want to generate this particular model from scratch, you can go to the repository tab. You can click on connect. And when you click on connect, you can expand the tutorials folder, and you will find here that the tutorial that I just created, this file that we just created, is available here. All you have to do is double click on it and run it. Okay. So what I'm going to do is I'm going to save the model file here, close it, and I'm just going to open the model that I just shared with you, which I already ran earlier. And when I ran it, I got a plot file, which is already here. All I have to do is click on this result. Yeah, for some reason it didn't find it, sorry. I renamed the file a moment ago. So I'll go to jobs and I can double click on it here. So here it is. It's a little bit less than 3 gigabytes. So you can see, it'll load it relatively quickly. And when it does, then what we're going to see is, I'm sorry, it's on a remote drive in my case. That's why it's taking a little bit longer than usual. If it's on the local disk drive, it would be faster, but I'm actually uploading it from the Google Drive in my particular case. Anyway, so here is now the actual model that ran, and I'm going to select an orthographic projection. And I'm going to select, for example, the nodal fluid velocity along the x direction. The nodal fluid velocity is, as you might expect, the solution for the fluid at the nodes. If you select the fluid velocity variable, it'll actually give you the velocity average within each element. So within each element, you would be able to see the average velocity. In this particular case, either one is fine. Let's say I look at the nodal velocity. I'm going to run this analysis, but in order to animate it, so I'll just show you, for example, here's what it looks like. I'll turn off the mesh. If I drag the time here, you can see that at first you have nice steady flow, but eventually it starts fluctuating, and eventually you can see this vortex shedding. So I can actually animate this by clicking on the play button, but if I do that, it'll run very slowly. So instead, I'm going to pick a fixed time step. I'll say 1 second. I'll go faster than the actual analysis. So if I click on this and I click play, this will run much faster than in 150 seconds because of the settings that I picked. But what you can see is, this is the analysis based on just the fluid velocity. So remember that what we're talking about here is vortex shedding. So it would make sense to perhaps look at the fluid vorticity, because this is a two-dimensional analysis. The fluid vorticity is in the z direction. So when you look at the vorticity in this particular case at this particular time, it has a magnitude of plus and minus 17.6. So instead, and so there's only a small domain that shows the vortices, because there's a lot of vortices formed right at the interface with the no-slip boundary. So instead, what I'm going to do is, instead of using the dynamic scaling for the legend, I'm going to let the maximum value be +1 and the minimum value be -1. When I do that, you can see that the vortices are much more pronounced. And if I press on the play button, you can see the vortex shedding. These are actual vortices since we're plotting the vorticity. So you can see the result of this particular analysis. I'll turn on the mesh again, so you can see that even though the mesh is a little bit coarser here, then the mesh density changes, but nevertheless, the analysis doesn't seem, you can't really tell by looking at the mesh that there's a change in the mesh density at this interface. It just seems seamless. So this just shows us the vorticity. And then if I want to look at the surface force that's acting on the cylinder, I only need to select one face of the cylinder because all the faces have the same value. It's the integrated force on the entire cylinder. I go to the post menu, I say new graph, and I select the fluid surface force. If I look at the X direction, it'll give me the drag force. And what you see here is the drag force initially, when you first start out, has a pretty large range. So I can actually change the range here. It'll turn out that, let's say if I go from 0 to 4e to the -6 in this particular case, you will see that this is the shape of the force. This has units of newtons in this particular case. So we're talking about on the order of 4 × 10⁻⁶ or 3.5 × 10⁻⁶ newtons. And if I look at the fluid force in the y direction, that would be the lift force. The net lift force, of course, is 0 on the cylinder, but these fluctuations occur because of the vortex shed. So normally what you can do then is you can say, well, that's great. This is the actual lift force in units of newtons, but what if I want the lift coefficient or the drag coefficient? So, I'm going to just continue here with this. So this is just showing you the slide for the result. Here, what you can do is the drag coefficient would be the force X divided by this quantity, which in our case, rho is 1,000, V is 0.01, and A is the projected area of the cylinder, which is 0.01 times 0.005, because we took 5 millimeters for the thickness of the domain. And when you do this calculation, then you do it in a spreadsheet typically, and you copy and paste, and you get the drag coefficient that you see here. And you can do the same for the lift coefficient. So the lift coefficient here is no longer in the order of 10⁻⁶ because it's a non-dimensional quantity. It's roughly between -0.35 and +0.35. And you can get what is called the Struhal number based on the periodicity of the vortex shedding. So you can actually get this frequency here, and you extract it and you multiply it by velocity divided by the diameter. And for this particular analysis, we get a value of approximately 0.17. So once again, this is just a summary of how we can create unsteady flow past the cylinder using FEBio. For those of you who have not seen this slide before, you can download FEBio from this website. We have executables for Windows, Linux, and Mac. You can also get the software directly from the source code from GitHub if you want to compile it yourself, if you want to modify it. These are our funding sources. And before I end this presentation, I want to show just one last thing. What if, let's say that you wanted to look at the streamlines? So I'm going to switch back to a standard view here. I'm going to turn off the display of the vortices. And I'm going to come back to maybe where we have the linear regime. I'm going to click on this icon to bring up the streamlines, and I'm going to select, for example, the nodal fluid velocity to look at the streamlines. But of course, when you look at the streamlines, they're hidden inside the material. So you have to make the material transparent, which you have to go to the material tab, select the material, and for the transparency here, you put 0. And when you do that, you can see that the streamlines will automatically show up, and you can animate these. And you can see the streamlines initially when the flow is very nice and laminar, and eventually when you're going to see slowly the vortex shedding. So you can see here that the streamlines become a little bit more curved. So this is just another feature of how we can display results in FE Bio Studio. Very good. I hope you enjoyed this presentation. And if you have any questions, you can actually go to the forum for FE Bio, which you can locate the forum from at this particular URL. I want to remind you that the FE Bio team currently includes Professor Jeffrey Weiss at the University of Utah, myself at Columbia University, Drs. Moss and Ellis, and Mr. Michael Heron also at the University of Utah. Thank you, everyone.